Hi everyone, my name is Arbligani, and in today's presentation we will discuss solutions for frequency constraints regarding grid-tied wind turbines. There are many constraints we must consider when connecting a wind turbine to the grid. In the US, our local power is operating at 60 Hz. In other countries such as Japan, the power transmitted operates at 50 Hz. We must also consider the active power met at the substation transformer we intend to connect, as the power output of the wind turbine too. Any mismatch between the two may cause issues. We must also filter out three-phase harmonics that may be generated as well. This includes noise and much more. Lastly, we must also control the reactive power to ensure a constant voltage output. Without any frequency control, the wind turbine's output shaft to the generator will rotate at a frequency dependent on the wind speed acting on the turbine itself. This leads to issues with synchronizing the electrical output to the grid, as the power will not always operate at 60 Hz. To mitigate this, DFIG controllers and power electronics can be used to clamp the output power to 60 Hz. So why use a doubly fed induction generator, otherwise known as a DFIG? They operate at roughly 90 to 95% efficiency of their available power output with better performance at their rated power output with a controlled algorithm of slipping the rotor to match the frequency of the stator. This dives into maximum power point transmission abilities, otherwise known as MPPT. The cost for the converters are relatively lower than other generators, as 100% of the available power is not transmitted to its output, but wearable items such as slip rings and brushes can add up throughout the lifespan of the turbine itself. For grid support, the DFIG treats the three-phase AC signals generated from the turbine as DC voltage links between the stator and the rotor to control the frequency in the Q axis and the reactive and active power in the D axis. There are two sides used for the DFIG. In the image shown, the box highlighted in blue features the rotor side, which uses the reference rotational speed omega r and the reference angle theta generated from the wind turbine. Power is then generated from the wind turbine and distributed as AC power to the leftmost side of the power transistor seen highlighted in blue. A clamping circuit then ensures that enough power is exerted at the rotor to match the frequency of the stator side. The stator side is measuring the reactive and active power along with the frequency of the power as a reference in order for the stator to match for grid hookup. With the simulation shown, the stator speed matches the frequency of the grid being 60 Hz. Depending on the wind speed seen, the rotor will either have to slow down or speed up to match the stator frequency by applying current to the brushes of the rotor, creating additional slip in either direction. Within the DFIG, there is a rotor and a stator that has current applied to its brushes to generate a change in the magnetic field to have the rotor slow down or speed up in order to match the rotational speed of the grid-side stator. For simplification, the part transform will be used to understand the physics behind the DFIG. The part transform converts the three-phase signals of A, B, and C to direct and quadrature axes. The D axis points in the direction of the magnetic field, and the Q axis is 90 degrees about it. This is important as it shows which direction torque will be applied and to quantify the amount of torque needed. For the Q axis, primarily used for the output frequency control, the reference speed omega r and the reference measured speed are then calculated for the error produced at the summing block. It will then go through the branches to form the equation seen for the current in the Q axis named IRQ. IRQ is a function linear to the amount of torque Te produced. NP is the number of pole pairs and psi s being the flux of the stator. This shows the amount of current required at the rotor to provide the necessary amount of torque needed to have the desired frequency output. The voltage across the rotor in the Q axis incorporates many voltage drops, resulting from our first term showing being the resistance of the rotor plus the stator's resistance multiplied by the rotor's current in the Q axis. Our second component is shown as the coupling component, which uses omega, the slip of the slip rings, multiplied by the inductance of the slip rings, multiplied by the current excited from the rotor in the D axis. The next term, L sigma didt IRQ, is a voltage component that shows how the leakage current L sigma resists the change of current at the rotor over time. The last two terms have to do with the voltage seen at the stator in the Q axis, being VSQ, and the back EMF component of the stator being negative omega times the flux component of the stator, which is psi. As the motor spins, there is a voltage opposing the source voltage on startup, which will eventually converge to a steady state voltage and reduce the current needed to reach the source voltage. As you can see here, picture shows the Q-axis rotor voltage using the equation for VRQ. Similarly, we can solve for the voltage across the rotor in the D-axis, resulting in the first term which quantifies the amount of current flowing against the resistance of the rotor and the stator. The second voltage drop can be seen as a component for coupling the reactive power needed by varying the slip frequency omega 2. The current at the rotor must then overcome the leakage inductance seen at the rotor to adjust the reactive power desired. Like the equation VRQ, the voltage across the rotor in the d-axis must apply enough current over time to overcome the inductance of the rotor. This means more voltage would be applied to the rotor in the d-axis. Looking back to the equation IRD, if more torque is applied, the more current is applied to the rotor, yielding a higher applied voltage. Lastly, the last two voltage drops considered are the grid-side stator voltage, Vs, in the d-axis minus the back EMF component of the stator being omega psi s times the stator resistance over the mutual inductance. As you can see, the controller used to base the d-axis rotor voltage can be seen here using equaling the equation seen for VRD. For our wind turbine simulation, we will be looking at the GE Verona GE 1.5 SLE wind turbine. The location we'll be choosing is Atlantic City, New Jersey, with a rated power of 1500 kilowatts, a diameter of 77 meters, a max speed of 20.4, and a voltage output of 690 volts, with a frequency of 60 Hz. For our wind values, we will be looking at the average per month of 2025 for the location of Atlantic City, New Jersey. These parameters can be entered into MATLAB using a doubly fed induction machine wind power system library in Simulink to simulate the expected behavior of the DFIG and its output. In this simulation, we have entered the 12 wind data points for our wind speed seen feeding the wind turbine, which will then calculate the expected mechanical power transmitted through the 1:72 gear ratio gearbox. The speed of the rotor connected to the output shaft is then used for the wind power controller to determine the power, torque, and speed demand. This is then fed as inputs to the rotor side converter to then accelerate or deaccelerate the rotor of the DFIG while using the grid side stator as a reference of the frequency you are attempting to match, which is in this case 60 Hz. As you can see, the top left graph shows the wind speed calculated at the nacelle of the turbine chosen. With only a sample size of 12 wind speed data points being average wind speed per month, we can gauge the power output to the grid on average. The top right graph shows the rotor speed increasing and decreasing based on the wind speed input for that index of time. This is the MPPT algorithm at work, ensuring that the peak power production is outputted to the grid while maintaining a 60 Hz frequency. The bottom left graph highlights the active power produced, showing a minimum of 0.15 pu and a peak active power of 0.37 pu. The dips are not variable, especially if you must meet a certain constraint in order to supply enough power to a load. A battery energy storage system, also known as BESS, can be used to mitigate these issues. Lastly, the bottom right graph highlights the net reactive power is absorbing from the grid rather than supplying reactive power due to a high inductance value. By decreasing the mutual inductance value, we can get closer and closer to a net neutral PU or supplying. Higher wind values could also help this case by having the wind turbine operate closer and closer to peak power production, as it will yield the best efficiency comparing the base value power versus actual power supplied to the grid. In the second simulation, we will change the wind parameters to the value seen in the wind miles per hour array shown. As you can see, increasing the wind speed yields better results regarding net active power and reactive power. Previously, the wind turbine was absorbing reactive power throughout the entirety of its 12-point cycle. With this change, the turbine is bouncing around 0 pu. However, there is a spike at month 5 due to the parameter set for the PID controller for the rotor side to match the reactive power of the grid side stator. To reduce the overshoot, lower proportional gain along with integral gain can be implemented. There are some pitfalls when using a DFIG for wind turbine grid connections. The cost of replacing mechanical components used to spin the rotor and stator can add up. Slip rings and brushes can wear out due to friction, heat generated, and current during the life cycle of the turbine. Continuous maintenance of the wind turbine will result in the turbine being inactive. This means less profit as you will not be able to supply and sell power to the utility company you are connected to. Harmonics play an important role when it comes to steady state power as well. The DFIG involves PWM switching to create a DC link between the rotor and stator, which can pose noise and must be filtered. Low pass, band pass, and high pass circuits must be used at both the stator and rotor side of the DFIG. Lastly, voltage drops and power surges pose an issue for the DFIG. The DFIG controller is dependent on the grid side stator parameters. If there happens to be an unintended variance between the voltage, current, apparent power, reactive power, frequency, and more, then there is a possibility that the rotor side's algorithm may adjust the speed of the rotor accordingly and damaging the components that may be out of spec due to the regular stator side power. To mitigate this, fuses and a crowbar circuit can be used to protect the power electronics used for the PID controllers of the DFIG. This allows for overvoltage protection. For this last slide, we will discuss the references used throughout this presentation. Reference 1 showcases the model doubly fed induction generator wind power system from MathWorks. This reference contains documentation on how to simulate a DFIG along with parameters needed to be changed to simulate a real-world wind turbine of your choice. The second reference shown is multi-physical domain modeling of a DFIG wind turbine system by Min Luo, which contains information of the physics behind a DFIG and how to simulate it as well. I hope you were all able to gather some information of one way to hook up a wind turbine to the grid with the known issue of wind turbines operating at a frequency dependent on the wind speed that is acting on it. Thank you all.